Okay, thank you and welcome everyone. So my name is Grzegorz. I'm an independent consultant and I do some trainings for Bottega IT Minds. And let's go straight to the topic because we don't have much time. So the topic for today is immutability. I'm sure you've heard this term for you've been hearing this term for quite a long time already because it's one of those big and hot things in the Java world. Because after years and years of being strictly OOP, and embracing less immutability and imperative programming in general, we figured out that there are other paradigms from which we can borrow good ideas from. And one of these turned out to be functional programming. I remember early days of Java when Mark Reinhold would go on stage on Java 1 and say that Java will never get lambda expressions because that would clutter the language too much. But as you can see, we are adopting more and more ideas like this. And Java is becoming quite more functional. But before we dive deeper into immutability and how complex this actually is, a quick test for you. So as you can see, there's a very simple method signature. It's a method called transform that accepts a list of strings, that returns a list of strings. And the question for you, let me tell you, what does it do? So I'm quite sure that based on the types, input, output types, and the name, you have certain intuition of what can be happening underneath. Any ideas? I didn't hear what you said, but certainly that's one of the valid options. Okay, any other ideas? Well, let me tell you, I actually ended up implementing this one. So you can just have a look. So as you can see, the method transform that takes a list of strings and returns a list of strings, it actually adds a new element to a list taken from some internal state of that class. It adds some constant to that list. It orders a pizza. It removes some elements from the list. If there is a matching lunar phase, it adds the list to some even more internal state and then mutates some static fields and returns the list. I bet you didn't expect this one. The problem is that the more we work with languages and tools that give us a lot of opportunities, a lot of possibilities, it's very easy to end up with a mess, with an unpredictable mess like this one. And this is quite hard to debug and follow, because once we interact with our source code, well, there is our, let's say, stacks are limited. We can't recurse that down inside to the bytecode level, to zeros and ones, the machine level, to make sure that everything is done just exactly as we expected. So often we need to stop at some point, generalize, and rely on names and, well, some abstractions. The problem is that if we don't pay attention too much how we craft our abstractions, and if we allow ourselves to do a lot of hacks like these ones, we end up pretty much with an unpredictable mess. I'm sure that at least once in your lifetime, you've been in a situation where you changed potentially something in your code that, well, seemingly wouldn't affect much, even if it was wrong. But for sure, there was a very distant part of the system that would stop working for no reason. And generally paying attention to the craft, to abstractions, and let's say restricting the number of potential states that you can put your application into kind of can contribute to fewer and fewer of such experiences. And this is where immutability helps a lot, because by restricting immutability of your abstractions, tools, variables, whatever, you can minimize the number of invalid states for your application. So a very simple example. If you take a very simple user PROIDEA, well, you create a user. The user has its properties. It has a name, surname, phone, something else. But now, from a perspective of a consumer of that API, which is the valid combination of properties that are acceptable by the class? Well, maybe the name is obligatory, but the surname is not. But phone might be obligatory as well. So, and I'm sure in most cases there will be no documentation that you can actually read about that. So even in such simple scenarios, by having your API designed this way, you expose yourself for quite a huge potential number of bugs because someone can just, for example, forget to set a mandatory field. So each field, each mutable field adds even more and more potential complexity and more of those invalid states for your application to be in. For those of you that have been around when Java util date was around, that was quite a lot of issues with it. For example, you could put a date into a hash set, change it over time, and then, oops, it's not there anymore. What we could do instead is just create a immutable user class, which has a name and surname as obligatory dependencies, and suddenly we reduce the error space drastically, because it turns out that, well, you create the user in one certain way without leaving too much of a possibility to making a mistake, without leaving too much, let's say, moving parts for you that can actually get broken. But immutability is also quite cool because it enables multiple kind of different optimizations. So imagine if you know that your object or something else is immutable, which means it can't change over time. Well, it can be pretty much memoized. Because if you know that your user named John is always the same user named John, why not just memoize it in reuse in many different scenarios? Which is another cool option is that if we know that the user is John and pretty much the object doesn't change anymore, we could pre-compute some properties like hash codes or presently size of a list. Because the list of 2 elements is always a list of 2 elements if it's immutable. Why actually keep recomputing this, let's say, on every .size call, if you know it at the beginning? What's quite interesting is that if you have a look at the JDK9 immutable collections that we got there, sometimes, you know, a list of 2 elements, it doesn't need to be an array list, it doesn't need to be a linked list underneath. It can be just 2 fields that simulate, that act like a list. Well, why? Because we know that this is a list of 2 elements. It will always be a list of 2 elements. So why bother having, let's say, the whole, infrastructure needed for setting up a proper linked list if you can just have 2 fields, which is good enough. But before we go further, a quick refresher on what does it mean for an object to be immutable, at least in the Java space. So according to Brian Getz from Java Concurrency in Practice, there are 3 things that make, let's say, objects immutable, at least in the context of Java. Object state cannot be modified after construction. All its fields need to be final, and that this reference can't escape during the construction phase. Okay, fair enough, but here comes a very important question for all of you. Is the string class immutable? Who thinks that the string is immutable? Okay, who thinks that string is not immutable? Okay, just to be fully sure, let's calibrate the room. So who is in the room? Okay, now let's see. Okay, so if you have a look from the what's been taught at universities on basic Java books, string is always used as a canonical example of an immutable the immutable class, because you can't really modify it unless you try really hard. You create a string. If you create substrings, you don't really modify the original one. You kind of derive new ones from it. But we had a look at the definition. Let's have a look at the internals of the string class itself. So we have private final byte array. We have private final byte coder. We have private int hash. Whoa, the int hash method, the field is not really final. And actually, it changes after construction because we are constructing the string class. The hash code, the int hash is there, but it's mutable. But then it gets overwritten when you call the hash code. What's going on? Did they lie to us? What do you think? It depends. So if you have a look at the immutability of abstractions and classes and objects, the true immutability doesn't really exist, because at the end of the day, those are our models, our abstractions that are run on this underlying impure imperative machine. Well, so it doesn't matter how hard you try crafting your abstractions, making them immutable. At the end of the day, there will be some data changing in one of the mutable registers of your CPU. And actually, even if you try really hard, you can mess up even your abstractions. So what's very important to remember is that immutability doesn't really exist, but what exists is immutability at certain abstraction levels. So it's perfectly okay for classes that pretend to be immutable to be mutable inside. They just never expose this internal state for consumers to use. So ideal immutable class or immutable object would never, from the external point of view, would always remain immutable, but can be mutable inside. But there is the problem, because which is the main, let's say, selling point of immutable collections or immutable data is that they're always thread safe, right? But if they have, let's say, internals that are moving, it creates a bit of problems, because it turns out that immutable objects are not always thread safe. And one of the classic examples is one of the, I think, Scala 2.11 bugs, where a new instance of a class or a vector could be actually perceived as a, let's say, in an invalid state by another thread at the same time. There was a problem because one of the fields was mutable and non-volatile. So some of you might argue that, well, if the implementation wasn't really thread safe, that means that the class shouldn't be even called immutable. But that is not the point here. I want you to be aware that even when you design something immutable, internally it can be mutable, and this can be prone to thread safety issues and various different bugs. And this generates complications like this one, where, well, the fact that we are running at impure machines kind of impacts our abstractions. So let's move slowly into how we could attempt design of immutable data structures and APIs. So the very common one example is a Java util list. Well, let's try to implement one of our interfaces to make something really immutable. But we quickly run into an issue, because the interface itself exposes a lot of methods like add, add all, remove, replace all, set, sort. And they don't really, and as you can see, what they return are some simple metadata or literally nothing. And this can be problematic because the only reasonable way to implement an interface like this is to, well, throw an exception. But this is not really cool, because now, as a consumers of our API, of this kind of immutable API, we need to be aware. We need to probably do some instance of check, or just as a precaution, just do a try catch, which is not a very nice thing to do. And what kind of functional languages figured out over time that the key to user-friendly APIs of immutable data structures are mutating methods. We still include them. But instead of returning metadata and throwing exceptions, we just return a copy of our data structure that actually contains a change that we asked for. So if we implement the immutable data structure, which is a list, you want to add an element to the immutable data structure. You don't really add it. You derive a new list from the previous one that contains the change you asked for. And this is very convenient. But it also has certain issues. It has a lot of problems. Because if you have a look at the implementations and the pseudocode implementations I did here, pretty much all of them start with copy with all, copy without, copy with replaced, copy and set, and so on and so on. So it becomes a bit difficult, because on the one hand, we know how we would like implement, let's say, how to implement conveniently the API, how to design the API of an immutable class. But now it becomes problematic, because that's actually quite a lot of copying and iterating, which is kind of not cool. Because if you remember basics of computer science, when we have an array list, when we have a set, when we have a hash map, we kind of expect certain time complexities from certain operations in there. And suddenly, if you want to create, let's say, if you have your immutable array list and you want to add a new element, and it involves copying of the whole previous collection and adding the new element, it kind of messes up everything a lot. And this is actually one of the prices that we need to pay for having abstractions like this one. So if you have a look at Haskell or purely functional languages, they actually generate quite a lot of garbage. So the ability to being able to run our beautiful, perfect models and abstractions is quite a lot of garbage. And this is okay, but we need to learn how to deal with it somehow. And this is where we slowly arrive to the topic of persistent data structures. And don't get me wrong, persistent doesn't mean that we will be storing something on a disk. It means that this is special kind of data structures where they are able to persist the previous versions of themselves. And this is, in general, this is the clue to being able to run actually immutable data structures at least a bit efficiently. So there, if you look at the scope of how this could be implemented, there are pretty much 3 ways we could do that. The first one we've seen already, which means we take a let's say seemingly normal API, and we introduce just a lot of copying. So we have a list of 2 elements. We add a new element. Instead, we get a new one by copying the previous one, and the previous one remains untouched. All good. But as you can see, it's not very efficient. It's quite the opposite. It's terrible. It generates a lot of garbage and takes a lot of time. What could we do else to prevent that? Another concept is the concept of fat nodes, which the easiest way to visualize it is to imagine like event sourcing, but for collections. Imagine having a list that records all the operations that happened on it, and then you can, based on that, recreate certain states of it during that time. And that's cool, but that introduces a lot of problems because that's effectively having huge memory leaks. And the third option, the most suitable one and most practical one, implemented pretty much by all functional languages out there, is the concept of structural sharing. So if you remember, at the beginning we said that if we have a value that's immutable, it can be memoized and reused. And this is the same idea, just taken much further, where you play with immutable APIs, but instead of creating full copies of them when mutating, you actually end up reusing as much as possible of what you have already. And this is pretty much what we'll be exploring right now. A few implementations of data structures that leverage those concepts. But before we do that, I'm not the first one to talk about the subject, but most of them kind of involve, let's say, overly enthusiastic and an ideal approach to this kind of, let's say, model. And Oleg Shalayev now works for Oracle. He did the same, kind of very similar one, very conceptual, a few years ago on Devox. And he illustrated the concept with this cartoonish unicorn symbolizing, those perfect recursive, let's say, immutable data structures that we are looking after. The problem, why I'm including it here, is that I believe it's not very scientifically correct. The image is, let's say, skipping over a few details. So after playing around with immutable data structures and persistent data structures, I figured out that the actual image is a bit closer to this one. So yes, they are beautiful, recursive, but they are not very friendly when it comes to our pure, impure and imperative machines. And I will show you why. So, but first, do you remember? We spoke about the string. We figured out that the string is immutable, but is it a persistent data structure? So if you have a look at the implementation of a substring method, you will figure out that, well, actually internally, the byte array containing all the characters doesn't change. So technically, we could reuse it, right? And this was the concept for quite a long time in Java. So whenever creating a substring of a new string, the old byte array would be reused and just logically capped by beginning index and length of the string. It turned out not being so ideal, so they ended up kind of keeping the solution, but still creating the copy of the particular chunk of the byte array. But you can easily imagine this actually getting implemented. The problem with this is that similar attempts were made at mutable data structures. So if you look at the array list, ArrayList also exposes a method called a sublist, which takes a beginning and end index. And this is also a logical cap. It doesn't really actually generate a copy. But this can lead to a lot of unexpected bugs that they are very hard to deal with and explore and find. So one of the real-life scenarios that I encountered in some tests is that we're taking a pretty much list of numbers, trying to shuffle them and check if one of the picked numbers was in the list of all the numbers. The problem with that is that somewhere along the way we used Guava transformers, which is a like pre-Java 8 stream-like ideas. Then we used sublist to like pretty much choose a few elements, and then we would just shuffle the whole list. And well, it was a bit of legacy code. I ended up rewriting quite a lot, and everything was green, which I found a bit surprising, because I would expect to make at least a few mistakes along the way. And it turned out the test would always pass, because the Java transformers, they don't generate copies. They return views over existing collections. And then we created sublists of those views. And then we shuffled the original collection, which ended effectively shuffling all of them. So we ended up testing if a few numbers are actually the part of the same collections, which would always pass, which was kind of cool. But and luckily, we didn't really have any problems on productions, but this is what could have easily happened. And this is how we slowly arrive at the actual design and how we can deal with, let's say, persistent data structures and implementing structural sharing in real life. So at the beginning, the easiest possible solution is the linked list. You might be a bit disappointed, but this is not the linked list you learned about at university. At universities, we learned that linked list is pretty much a collection of nodes linked together using some references. Here is pretty much the same, but the structure changes a bit. So instead of referencing nodes, our nodes are referencing previous versions of the same list. So imagine a simple list containing one element and a reference to the previous versions of the list. So if you have a list of 2 elements and you want to add a new element, you create a new list which holds the new element and points out the previous version of the list. Very simple, very effective, and actually works. So if you have a look at, if you create, for example, a simple list of 0 elements, if you add a new element, you never modify the original one, and you create the new one by composing previous version of the list with the new element. And this actually works. It doesn't involve any copying, and provides constant time as well, because addition of a new element involves creation of a new node and just pointing out to the previous version of the list. Cool? Is all good? But here the first problems appear. What about list append method? Because we know that we have this recursive list we can add from one element efficiently and reuse the previous one. What if we want to add an element from the other side of the list? Now it's not so obvious, and it's not so cool, because, well, the structure that was here in the past allowed us to add elements from one side efficiently, but it's not so easy when it comes if you want to access the list from the other side and add something there. And this is actually very sad, because now it turns out that the time complexity will be totally different for a list append and list prepend. Now it's no longer constant time, it's linear time. But we can somehow live with that because, well, mostly we add to list from one side all the time, which is kind of okay. And this is usually when people start asking questions regarding thread safety of such data structures. Because if we have this complex, let's say, recursive data structure, which keeps pointers to previous versions of itself, imagine you have 2 threads jumping in and are trying to modify it at the same time. So who gets what part, and how do we ensure thread safety of this? The tricky part here is that we don't think about this, because the data we are operating on is immutable. So you never share data structure, you share the value. And if there are 2 threads jumping into one value and adding elements to it, they always do it in their own scope. They derive new values from it, they never modify the original one. But this is the point where usually I think kind of gets overlooked. Immutable data structures and immutability is promised to solve our problems of thread safety. And it does, but it turns out that in a very, very nazi way. If you remember the story of King Midas, who really wanted to have to touch everything and be able to change it into gold, well, it didn't work out very well for him, because it turned out that once he obtained the power, well, he ended up touching food, drinks, family, and everything turned into gold. It's a bit the same with immutability. Of course, immutability gives you thread safety, but gives you thread safety by not allowing you to share updates between threads. So we could say the same about removing multi-threading from Java. We wouldn't have problems with concurrency because you have everything running in a single thread. Good luck with that. So if you really want to play around with immutability and concurrency, if you want to use immutable data structures for concurrency, you need to kind of manually manage the access to them. So imagine you have an immutable list that you really want to use as some form of a queue or something else, and you only want to share those updates between other threads. Now suddenly, let's say those magical aspects of immutability and thread safety is no longer visible, because it turns out that firstly you need to have a mutable field, which you will be replacing with the new versions of an immutable data structure, and then you need to write your own, let's say, concurrent-friendly code that would do that. So as you can see, we were supposed to not touch concurrency. It was supposed to be solved for us, but it not actually is. So what can we do? Well, in most cases, I would tell you to just use a dedicated mutable data structure, because immutability that is not applicable everywhere. Sometimes if you want to share updates between threads, it's easier to use a concurrent-friendly data structure that we have in Java util concurrent package. Or maybe use a different way of sharing updates, which is also an option. To make it easier to visualize to you, imagine that you want to have a shared string instance and for multiple threads to be able to append to it. That wouldn't be really easy. You still need to write quite a lot of not a lot of concurrent code, but you need to worry about concurrency managing it by yourself, which is not cool. And so even though you have thread safety, you have those big synchronized blocks all around the place. Maybe some of you will try to fight with it and apply, let's say, lock-free approach to that. And it becomes even harder. I mean, it becomes a bit easier, but imagine that you have 1,000 threads trying to update a shared immutable list. 1,000 threads make update at the same time, but only one can actually swap the implementation of a list with the new one. So n minus 1 threads needs to abandon the current instances and retry the operation. And all those instances generated and not actually swapped with the original one end up being thrown at the garbage collector, which stresses it a lot. So as you can see, there's quite a lot of trade-offs everywhere involved here. So all good. We've seen the basic ideas for the structural sharing when it comes to an immutable list, and pretty much by having a list that points to previous versions of itself. And that if you have a look at, let's say, the waiver library, if you have a look at Scala or other languages like this, or Haskell, this is how you implement a list, and this is commonly used. But this is okay, because it gives us, let's say, some complexities we would expect from a list, more or less. But what if we want to implement a persistent set, an efficient immutable set? Well, the easiest way to do that is to pretty much keep a list underneath. But again, that's probably not good enough because we would have an ON element access. But for sets, we kind of expect something better. Let's say something with the logarithms, at least. The question is, could we do something smarter than that? Keep in mind that I use the word smarter, not necessarily better. We could use a tree. So if you have a look at the scope of data structures, trees are also in its structure kind of recursive. So any node in this list, in this tree that you see over there, could be potentially a tree on its own. So there is some potential for structural sharing over in there. However, the way we add elements to trees makes it very hard to have a full reuse. So whenever we want to add elements to a immutable tree, persistent tree, there will be always a bit of almost always a bit of copying and unnecessary iterating involved. So let's say, imagine we want to add the number 42 to this tree. We would need to effectively go to the very beginning, to the leaf node, add a 42 in there, and then we pretty much replay the whole structure till the root itself, which is not cool, but works pretty fine if you have a bigger structures, because pretty much all which is black on this image can be fully and safely reused. But you can already see we are slowly running into a space where we have a lot of trade-offs to manage, and we can't even get close to what we have if we actually try working with pure, impure, and imperative mutable data structures. So we know how to make a list. We know how a bit complex the set is becoming. Let's try to imagine how we would implement a persistent queue. Well, the linked list is a queue. Actually, it implements a queue interface in Java. But it turns out we could use a linked list, right? I mean, persistent singly linked list. There's one problem with that. It would work great really as a stack if we are adding and taking elements from one side. But think about it. How do you work with a queue in general? Usually we put things from one side and take things from the other, which means that we would constantly end up with the problem that taking things from one side is constant time, but putting things from the other side is actually linear time, which is a bit unacceptable for a queue. So what could we do in order to make it better? And probably the easiest solution out there, if you take a definition of a persistent data structure, if you take a definition of a queue, at least from a time complexity point of view, what can you do to make it work? Well, we could take two single linked lists, and put them together against each other, just in reverse. So in this way, what we can achieve is that we can easily add elements from both sides and remove in linear in constant time. However, from time to time, we ending up having them imbalanced, or one of them running out of elements. And this is where we actually need to reverse and rebalance them. So in most cases, that would be constant time, but from time to time, we would end up in a situation where we need to rebalance it. So if you do some kind of black math magic, you can prove that this is an amortized constant time, which means this is constant time, but not really, because from time to time we have an ON operation involved. But this is already quite a huge improvement over a simple linked list if we use it as a queue. But most likely this kind of implementation wouldn't be suitable for real-time systems where you want to have a predictable latency. The question is, again, could we do something a bit smarter than that? Well, we could use a tree. It turns out there is a data structure which serves as an ideal queue. So it's based on the idea of a 2-3 tree. A 2-3 tree is a kind of special tree which has a 2 or 3 branching factor, and then stores all the data, let's say, at the same level. But you might be asking now, Grzegorz, you promised a constant time access to the beginning and the end of the queue. How are we supposed to use a tree for that if we know that accessing elements in a tree has something to do with logarithms, at least in there? The trick that data structure is used is actually to take references to the, let's say, particular leaves and pull them up to the root itself. So we ended up having this old school data structure just kind of reorganized so that the root contains the pointers to the first and the last element. And now we have constant time access to the first and last one. But we have an issue. Because imagine, how would you implement an operation, let's say, of a removal of an element? If you remove an element from the, let's say, from the last element from a such tree, such queue, you have a hole in there at the top that needs to be filled with an item, with a node that's below it. So you move this item that's below it, put it up, but then you have another hole, and so on and so on. So again, just like in the previous example, we are ending up with an amortized constant time, but really not true constant time as we would have for a real mutable simple queues. And now a very important question. If that solution is so smart and ideal, why do you think that Scala and other languages, they use the banker's queue, the simple solution with 2 lists instead of the complicated tree? Because that's indeed the case. Maybe not in all languages. Haskell has 2 3-finger trees, but let's say Scala and others prefer a simple banker's queue. Why do you think this is the case? Who of you went to Tomek Borek's presentation? A slot earlier. None of you. 1 person. Okay, now it's all enough. Okay, do you remember what's the difference between an array list and linked list? Why linked lists are not that used a lot, at least in Java? Usually, when we need to make this kind of a distinction, the answer is very simple. It's performance. The issue, if you compare the performance of an array list versus the performance of a linked list, you will see that linked list performs much slower, mostly because of a cache and friendliness that it introduces. So if you need to jump from one node to node to node to a node, you need to do quite a lot of pointer dereferencing, which is quite expensive, because every such call will most likely those calls will involve cache misses. And this kind of the data is distributed on a heap in probably unpredictable places. So you need to keep jumping from a place to place to place and involve quite a lot of cache misses. While if you are iterating over an array, a CPU can do quite a lot of magic. If the CPU sees that you are iterating over an array, it will say, okay, I see you are iterating over an array, so let me prefetch the data that you should most likely encounter in the future and put it in my cache. And this is why array list ends up being much faster than linked list. And now, look at this solution. The problem with linked list was that there was a jumping between nodes with values involved. And look at this one. Again, there's quite a lot of nodes that don't have any value. They are only there to make sure that the data structure works. So imagine if you want to access an element and next iterate for a list, for an object like this one, that would involve quite a lot of jumping over a lot of nodes. And many of those nodes would not even contain values. So it turns out that this ideal persistent queue based on 2 3-finger trees turns out being much slower than this potentially dumb and naive solution based on just 2 lists put together. Quite interesting, right? And the holy grail of persistent data structures, which is a persistent attempt at a hash map. So naturally, if we wanted to get something that acts like a hash map, that would be as easy as just putting a list of entries within a map. That would work. That would work just very slow. Could we do something better than that? And the holy grail of, let's say, persistent data structures are one of the variations of hash array mapped trie. And just to let you know, this is not me making a typo. It's spelled T-R-I-E. It's a trie, not a tree. In other words, it's called Radix Tree. So if you remember stuff from university classes, for sure remember finite automates. And this is kind of this idea. So a trie or a radix tree stores is used for storing, let's say, prefixes of strings, like in a bit oversimplified manner. So if you, and this can be, for example, used for, let's say, implementing various searches. So if you want to find all, let's say, strings that are prefixed with this particular one, that this kind of data structure would be very convenient to use, because you could just jump to a particular node and return all children of that particular node. And those are all strings that are prefixed by this particular one. Okay, but how does this relate to the concept of a hash map and immutability and persistent data structures? Because it turns out that the trick to do the hash map is to use the Radix tree, but instead of storing random strings, is to store hash codes. So imagine that we split hash codes into a few chunks, and each part of the hash code is responsible for one of those, let's say, traversals between nodes. And now you can for sure, let's say, encode, let's say, access to particular elements using their hash codes. Each node internally would have an array, which would be used pretty much, which could be used for lookups based on the hash of this particular node, and all of that can work. But again, you might tell me, but hash map is promising us constant time access for elements, and this is again a tree and not something that gives us constant time access. But there is a trick that we can use over there. So this kind of data structures, they use extremely high branching factors, like 32, for example. So each node can have 32 subnodes. And further, we can play around with space efficiency, because you might be worried that we might have a lot of empty arrays, but this can be used, let's say, mitigated using bitmaps. But the trick I wanted to remember is that there are those incredibly high wide branching factors. So a very quick question then. Do you remember what's the value of logarithm with the base 32 of n elements, where n is, let's say, integer max value? That's not a big number. It turns out that this is actually 6 point something. So even though we have this tree-like data structure, which doesn't give you a constant time, of course, lookups, but with the branching factor of 32, this tree will be kind of a shallow. It won't be ever bigger than 6 or 7 layers, which gives us a bit predictable, let's say, results when it comes to time complexity. Of course, it's still a log n based lookup, but we know that it will not involve more than 6 or 7 hops at most. Even if we wanted to store, let's say, long max value, that would be max of 13 hops. So it's still a bit inefficient in comparison to the classic hash map, but this is pretty much the best we can do when it comes to playing around with immutable data structures. There are various variations on the topic, and the new one was implemented in Scala pretty much like a month ago, which is the compressed hash array mapped prefix tree, which is a bit of a different variation on that. If you start digging deeper and deeper and deeper, you can find a lot of interesting white papers about concepts that are trying to make it both cache-aware, immutable, and fighting, pretty much chasing all of those nice qualities that we would get for our standard mutable and concurrent-friendly data structures. So as you can see, making things immutable involves quite a lot of complexity, and it doesn't really simplify things that much as you would expect. If you would like to play around with, let's say, and see around how they are implemented and play around with data structures like this, you have pretty much 2 libraries on the market that you can use. You have Waver and Cyclops. I'll tell you to use Waver because it follows the Scala a bit more. So at some point, if you are coming from the Scala environment and going to Java, you will find a lot of familiar things in Waver. But if you are going from Java through Waver to Scala, your job will be a bit simpler. There's also a Cyclops, which is really cool, but let's say it has its own opinions on things. So I would say try with Waver first. And when it comes to today's talk, I'd like you to remember just a few things. It turns out that immutability is much more complex than you might think. So efficient immutability involves, in the pragmatic aspect, minimization of copying and maximization of structural sharing of elements that we do between those data structures. This is of course involves quite a lot of trade-offs because those elements that are the part of those data structures can't be released anymore. So we end up using a bit more memory than we would use if we worked with mutable data structures. Another takeaway is that simple solutions often beat complex ones. So sometimes even those most ideal models that we have, we need to remember that they are still being run on machines that are impure. And we need to take that into consideration while designing things, if we want to, let's say, get the best results of our software. Again, immutability, you might not be surprised, it's not a silver bullet. There are still scenarios where mutable data structures beat immutable. For example, concurrency. Don't try to force immutability to work with concurrency because you might have a hard time. And trade-offs are everywhere. So usually when you find a golden solution that gives you a lot of benefits, in most cases it will have drawbacks that you will need to worry about. And that's pretty much all. On the slides, you can see a bit of references and some interesting, let's say, white papers and articles. The one that I'd like you to look at is the last one, which is an article from Alexei Shipilev, who proves that actually runtimes that have garbage collection can actually improve performance over, let's say, simple and non-managed languages. So thank you very much, and I hope you learned something